Hi, I'm Burke, and I'm going to be presenting on behalf of my team. Our project is about developing infrastructure for running, evaluating, and applying machine learning models for predicting side effects from the chemical structures of drugs. Our sponsor is Pfizer, and our advisor is Professor Aguirre. The premise of our project is that the drug development process is extremely expensive, and often millions of dollars can be wasted on a drug that looks promising, but months down the line in clinical testing turns out to cause some terrible side effects. The role that computer scientists want to take here is to predict these side effects using machine learning before all this time and money are wasted. There have been plenty of models that try to do this, but no one's looked very deeply at how well they do as a whole. How much progress has the field made? So we're given chemicals like these. How do we predict their side effects from just their chemical structure? First, most methods translate them into a binary vector called a molecular fingerprint. There are other ways we're looking at to do this. For example, a bag of bonds representation borrowed from natural language processing. But we're sticking with fingerprints for now. So next, we feed these vectors into a machine learning model, like a random forest, that predicts its side effects. But we're interested in taking a holistic view, so we actually run a bunch of models all together. Once we have this, we analyze how well these models predict certain side effects, some better than others, and we do the same thing for the chemical space of drugs. A very important part of this flow, and the one that's the trickiest to handle, is how we get good data of drug side effect associations in order to train our models. One of the data sets we work with is called FAIRS. This is a public database where doctors enter in their patients' prescriptions and any side effects they experience. This is a big and messy set of data, and we've spent a lot of time making sure it's as clean, interpretable, and statistically informative as possible. So in implementing this workflow, we made several improvements that can be used both in industry and science. We've created a pipeline that processes the complex data in FAIRS in a principled way. We've also re-implemented several machine learning models from papers over the past 10 years and standardized and brought them under a single API in Python. Together, these two angles allow us and potentially drug developers to easily import data and train and apply half a dozen machine learning models at once in just a few lines of code. We ran this pipeline on some data, and we noticed that, at least in terms of a metric called the area under the ROC curve, or AUC for short, the state-of-the-art can predict side effects pretty well. So most papers evaluate their models in terms of this metric, except take a look at this model. It's one that just predicts the empirical frequencies of side effects, completely ignoring chemistry. And from certain angles, it seems to do just about as well as the actual models. In fact, we've mathematically proved some statistical properties of this dummy classifier that shows just how misleading current evaluations of side effect models are. We also ran some simulations to illustrate this in a pretty way. Now we're showing how to evaluate models in a way that keeps this pitfall in mind. For example, here we see clearly that although certain current models have some skill, it's nowhere near as impressive as it first seemed. Instead of aggregating accuracy down to a single number like people normally do in this field, we're taking a closer look at what the models can and can't do at the chemical level. We've created a visualization for drug developers of the chemical space of drugs, colored by our accuracy in predicting each one using a variety of models. In the visualization, you can select your models from the drop-down menu. And then once you select one, you can rotate around the chemical space and pick out the drugs that might be of interest to you. Here's all of us all together with our advisor, Professor Aguirre. We all wanted to say thank you to the School of Engineering and to Pfizer for this opportunity to work on such a cool project.